In the previous video we estimated one OLS equation for one out of our 10,000 data sets. So now we're going to do this for all 10,000 data sets, but the code is going to be very similar, so I'm going to copy it. And we're going to be using it here to generate 10,000 different slopes, which gives me the distribution of the slopes. So let's make a code block. So I'm going to keep track of the constants. So I create them as an empty list. I'm going to keep track of the slopes, which I'm also going to create as an empty list. And now what we're going to do is we're going to say that for I in the range of n simulations, so basically I is going to go from 0 till 10,000, but not including 10,000. And I'm going to paste what I just copied. Oops. So I'm going to, for each I in this range, I'm going to have this model, which is an OLS estimation. Now not of only the first, but I'm going to do it for each I of the data set that we have. So for each I, I'm going to have 20 Y observations and 20 X observations. And it means that for each I, I'm going to estimate slope. So then I want to know the parameters that go with that model. Same way we did before. And then we're going to say, oops, constants dot append. I'm going to use the append function, which simply adds another observation to the list constants. And that's going to be from parameters, as we saw above, the first element, which has index 0. And we're going to do slopes dot append, and again from params, that's going to be the second element, which has index 1. Oops, used the wrong bracket. Yep, so I'm going to run this code. So that will take a bit of time, but we can simply keep on typing. So then I want to have a histogram to get an idea of the distribution of the slopes. So in the notebook you also have to give the histogram of the constants, but I guess if you see how I do it with the slopes, you're going to be able to do this yourself with the constants. So again, I want the density, not the absolute numbers, and we're going to have 50 bins. Oops. So I'm going to have an X label, which is slope. We can have a Y label, which is frequency. So this is the distribution of the slopes that we have. So as you can see, on average the slope is around 2. Yeah, so you can compare this with the way we generated the data, the slope that we specified when we were generating the data. But it's not the case that in each OLS regression that you run you're going to find the slope 2. Sometimes you can find the slope of minus 2.4, other times you can actually find one with 1.6. So there is a distribution around the true parameter, which in our case was indeed minus 2. So this is one way to look at the distribution of the slopes. There's another way in which we can look at this. And that is to plot the different lines simply in X, Y space. So what we can do is we can say that for I in range, just to limit the amount of time that's needed here, I'm going to only plot it for the first 50 data sets that we have. So you can plot it yourself for the 10,000 that we have, but it's going to take quite a while. So I'm going to plot each of these lines, and again, as we did above, because it's a line, I only actually need 2 points, so I'm going to use for the X variable just the points -2, +2, and then we need to specify the y coordinates for each of these cases, so that's going to be constants I plus slopes I times -2. So that's the first y coordinate. The second y coordinate is the same, but then multiplied by +2. Let me see, the brackets look fine. Yep, it should work. So then we can again have x label, and in this plot the x label is simply x itself, and the y label is going to be y itself. And here you see all the different lines that we have estimated in different colors. Yeah, so you see that there is not a unique line, there are a number of them. There is some variation in the lines that we estimate. As you go to the outskirts of the graph, so the -2 and the +2, there is quite a bit of variance, so we don't know exactly what the y coordinate is going to be for when x is equal to 2. But for x around 0, we're actually pretty sure about what y is. So I'll leave it to you to figure out what's so special about x being 0 and y being 0 in this plot, that we have less uncertainty about points over here than we have about points at the end of the interval.